All right, the example we're going to do this time is the polyatomic ion SF4-. This will actually illustrate a couple of finer points about Lewis structure. So going through the steps that I've been trying to impose on you, it's not an ionic compound, so you don't have to separate them, although it is a polyatomic ion. So the next step is to count up all the valence electrons that you have. So the sulfur is going to contribute 6 electrons. Each fluorine contributes 7 valence electrons, and then because it's actually this is a -2 ion, and we're going to have 2 more from that, which gives us 36 valence electrons to use to hold together those 5 atoms. So the formula would indicate that sulfur's in the middle. And the 4 fluorines are peripheral. So we've used 8 of our 36 electrons already with these single bonds. So the next step is to put 3 unshared pairs around all of the outer atoms that are not hydrogen. And so we can start. So we've got 8 showing now. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And we still have 4 electrons to distribute. So the next rule is that if you have any left over, to put them on the central atom. So that sulfur in the middle is 2 unshared pairs, the remaining 4. And this is our base skeletal structure. Now let's see how things are here. From an octet standpoint, remember for octet counting, you count all of the shared electrons. Each fluorine, by that counting scheme, has the octet that it wants, the 8, so that's good. And the sulfur also, 1, 2, 3, 4, 5, 6, 7, 8, has a filled octet as well. So from an octet standpoint, this is actually a pretty good structure. Now the other thing that you want to make sure that you're aware of is that the formal charges are kind of what they should be. And remember, the difference for formal charge electron counting is that you split up the shared electron pairs. So from that standpoint, let's look at the fluorines again. So we've got 1, 2, 3, 4, 5, 6, and then 7 electrons that we can assign to the fluorines. Fluorine usually has 7 valence electrons, so the formal charges on all of these are in fact 0, which is good. Now let's look at the sulfur in the middle. You can assign 1, 2, 3, 4, 5, 6 valence electrons to sulfur in there. Now sulfur is in the oxygen group, so it normally has 4 valence electrons. It has 6 in the structure, which means that the formal charge on the sulfur is -2. Now remember that the formal charges of all the formal charges need to add up to the overall charge of the species, which is what we have here. The question is that where it needs to be? Now I have told you that one rule is that to put negative formal charges on the more electronegative element. And I've also told you that fluorine is the most electronegative element there is. So this might seem like it's a problem. Now the magnitude of the formal charge is as low as it's going to be, -2. But can we redirect that formal charge to the fluorine atoms that are more electronegative than sulfur? And the answer in this case is no, because fixing this would make you break one of the 2 rules I told you to never ever break. What you would need to do is move more electrons to fluorine. So let's say take some away from the sulfur and do that. That would lower the formal charge on the sulfur, increase the formal charge on that fluorine, but it would also mean you have exceeded the octet rule on a group 2 element, fluorine, which you can never ever do. So this is actually the best you can do for this species. And truth be known, sulfur is a reasonably electronegative element itself, so the -2 formal charge on there isn't that bad. You probably don't want to do this for metals, but for most structures that represent real compounds, you're not going to see that anyway. Now, what does this molecule look like? So we have 6 electron domains around that central sulfur. So the electronic geometry is going to be octahedral. 2 of the 6 electron domains are the unshared pairs. So the molecular geometry that we learned for that particular case is square planar. And what this would actually look like is I'm just going to put the lone pairs as being above and below the plane of, or in the plane of the board, above and below the sulfur. The fluorines and the sulfur would all be in the same plane, in this case the plane parallel to the floor and perpendicular to the board. And that's what it looks like.